planets that you see here have moved. They have moved closer. There is a couple of mechanisms that produce this, migrations or dynamical interactions. Well, you would see that some of them have not moved very much, which are this one here. We have Jupiter quite far away. So we have found, in a way, similar planets to Jupiter, but this is only a small number of them. Most of them have been found very close to the star. Well, in the radius, if you look at the radius, there is no planet here. You see in this region that is matching the red planet there. The reason why is because the transit techniques, which is giving you the radius, doesn't work. It's essentially very unlikely that the alignment between you, the star, and the planet will be good enough to see a transit. So the probability is just a matter of likelihood here, becomes so low that even if you have a significant amount of planet, you need so many stars to find some that you end up with very few. This is why there is no planets, but there are plenty of planets here, because you see them here in techniques which is used to sense the mass, which is not that sensitive to this. Now, if you want to understand the rate of occurrence, I mean, what is a likelihood that you have a planet on a star, you have to do quite sophisticated statistical analysis. It's not visible on that diagram, but I just show you the result here, and the result is essentially this number. Just get, yeah, here. So this is a number that tells you, if you observe a stars, what is your chance that you have a planet? So you see that the one that we have called the hot Jupiter, because they are this roasted Jupiter, like 51 Peg B, are not very common, 1 to 5%. That's about the chance. Well, you have about 10%, up to 50% of chance to have a Jupiter. 50% is, it depends what you define as the upper mass. I mean, here you see there is a lot of planets that are more massive than Jupiter. It also was a big surprise because Jupiter was understood to be very big, but they are even bigger planet than Jupiter. And it depends how far you go. There are systems, especially the few systems where we have a picture, have been found very far away, much farther away than the orbit of Uranus and Neptune. So we can end up with quite a significant amount of big planet here, but the really big surprise was the fact that we have found this massive amount of what we call super Earth, because we don't really know what they are. They are sitting not at the Earth, just beyond the Earth, but most of them are sitting below Uranus and Neptune. We could have called them mini Neptune as well, but super Earth is kind of cooler. That's maybe why I think people have decided to call it super Earth. And this is a massive amount of planet. About half of the star, even to 80% of the star, they do have such a system. So I think this was a kind of a summary of 25 years of research that told us a story that is, the solar system is not the dominant kind of planet in the universe. We don't know how rare it is because we have missed right now the solar system. It's not because they don't exist. You see then the Earth and Venus is quite alone in this diagram. It's because it's very difficult to detect them. So let's see that as a gift of nature. If they would only exist planets like our own, we would end up with very few. The transit would have been a catastrophe. So essentially, the Kepler mission would have found very little planet, and we would not have been so lucky to find early on this planet 25 years ago, because there is very few of such a systems, and you need much more time. So it's a piece of luck, but it's also a big question mark. Why then the solar system is how it is? And frankly, we don't really know the answer. But this is something fascinating to think about, that we are not the vast majority of the system. Now, the other diagram I want to show you here is the one which is tell you about the density of this system. So we know when you combine the mass and the size, oops, sorry, what's going on here? Yeah, the mass and the size, that you have a huge diversity of system going from the giant planet down to the very small planet. So what is very interesting here is to overlay structure of this planet. This is the structure of Jupiter, you see here, and you see Jupiter and Saturn lie quite along this, and we have a lot of other planets slightly above because they are hotter, so there's more energy and a bit inflated. Then you're hitting the structure of Uranus and Neptune. It's essentially water density planet, and you see where they are. So this is where they would lie. If you would be of an Earth density like, you will be along the green line here. And you see that we have a diversity of planets, and when you hit the very small object, like 5 to 10 Earth mass object, you can end up with a planet that is like the Earth. This means along the green line here. You can end up along the line a planet which is like a water, or you can end up with a planet like is like a Jupiter. So that was a really big surprise. That having small planet doesn't mean they are all like the Earth. You can end up with fascinating worlds that have a very thick atmosphere or immense oceans of maybe 2,000 kilometers deep, or in some case you can even have a rocky planet with immense oceans. On the top you can even have hydrogen gas, that is this one here. So the planets are way more diverse than you think. So if you're writing sci-fi movie, I think you can really invent any planet you like, because this is what it is, the reality. There are all kinds of planets you can imagine, and we're trying to figure out exactly, oh wow, we have so much diversity here. And this is one of the big challenges on the current programs. Now, what I would like to convey to you is we can do way more than just getting the mass on the side. We can measure the atmosphere of this planet. How we do that? We have the transit of the planet, and this is a light curve. This is the light from a star at the time you have a transit, and you have a big transit here at the time, but you have also the time when the planet goes behind the star, which is called a secondary eclipse. It's eclipse usually when the planet is behind. Now, what you have here is, this is a zoom. You have this very location here. This is the eclipse when the planet is behind. So if you think about that, when the planet is behind, it means you only see the star. This is the real flux from the star. This tiny moment here, that's the only moment when you see only the star. It means all the other time you see the star and the planet. Now, if you think about that, you have then here the location of the star, and anything which is above it is coming from the planet. And we're using that kind of light curves on transiting planets, and the fact we detect this moment to see that all the other flux is coming from the star, from the planet. This is how we can tell you what is like the atmosphere or the surface of a planet. So if you think about that, they are very far away. All these systems are very far away. We're not going to go there, but by just looking at them, looking cleverly at them, we can tell you what is about the atmosphere, what is about the surface of this planet. And I think this is a fascinating prospect, because we have thousands of planets where we can do that potentially. Now, I would like to open another chapter, which is quite often in the press. It's the concept of habitable zone. So habitable zone is quite often mentioned as the key to think about life on this planet. Well, what habitable zone tells you is essentially if there is water, and most of the time we don't know if there is water. Let's imagine you have water on the planet. Well, this water is in a liquid form, is not evaporated, it has not dried out. Well, it requires specific locations. If you're too close to the star, you will evaporate the water. If you're too far away, you still have plenty of water, but it will be in solid form, it will be ice. Well, we assume that to bear life, to develop life, is not a valid starting point. So you define a region that, of course, depends quite a lot of the atmosphere you assume. If you have a lot of greenhouse effect, if you have little greenhouse effect, it depends of the synergy between the planet and the atmosphere. It depends the kind of atmosphere, if there is hydrogen or not in the atmosphere. But without all this detail, there is still a range.
YouTube ಅಂತ ನನಗೆ ಕಳಿಸಿ ಇಲ್ಲಿ.
Sorry, can I continue?
Yeah, sure.
Okay, so this habitable zone defines a region where you can sit and have this liquid water. So essentially the problem we have right now with this habitable zone is all the planets we have found on solar type stars, they are very close to the stars. So they are not in the habitable zone. But we're trying to trick the system by looking at planets on smaller stars. If you look at smaller stars, then the star gets cooler, and then you enter into a regime where the habitable zone gets closer and closer and closer. So that's why right now there is a strong interest to look for planet orbiting star smaller than the sun. We call that M stars. And you may have seen quite a lot of this announcement where planet has been found. There is a couple of examples here that is called in the habitable zone with a low mass stars as a host. It's a bit of different stars. It may be a bit different in terms of consequences of the impact between the atmosphere of the planet and the star. But it's good for you to think about that. I mean, a lot of planet may be within the habitable zone, but the star is very different. And there are plenty of these low mass stars. Essentially, the galaxy is full of small mass stars. So we have potentially millions and millions of planets that are within the habitable zone due to that reason here. Now, what I would like to just briefly mention to you, astronomers can measure remotely the atmosphere on these planets. We have started doing that. We will be doing that even more in the future with the James Webb Space Telescopes. This is the kind of atmosphere we're hoping to detect. We're hoping to detect features like oxygens, methanes, carbon dioxides. All these elements here can be measured because they imprint a sign into the emission of the planet, or when you have the planet crossing the star, having in the transit, you can have some grazing light that is being affected by this molecular line, and you will be seeing it. We have been detecting water on giant hot planet already. This is an old topic. It has been done 5 years ago already. So we know how to do that on big planets. What we're trying to do right now is trying to do that on smaller planets. And that's more challenging, but we will have great machine. One of them will soon be launched. It's called James Webb Space Telescopes. We're also building up very large telescope on the ground. There's a couple of these giant being built right now that will help us to do that. So essentially, if you detect oxygen, water, or CO2, you can learn a lot about the atmosphere of the planet. Most of the time, it will not tell you that there is life because you can produce oxygen by breaking the water molecules. So you have a lot of different mechanisms that can create oxygen. So don't get the feeling that if you have oxygen, it's only produced by biological entities. But what is really interesting here is you can use the global knowledge trying to build a full geophysical model of what's going on the planet. And this is what we're going to do. We're going to combine the astrophysical information that you can retrieve from this atmosphere and from the fact you know the mass, you know the size of the planet, you know quite a lot on the planet, to try to find out what is the geophysical complex model you can build on the planet. And in some case, and one of the cases here which is mentioned in the Earth, to produce a clear-cut biological identifications, there is a series of molecules that you will need to argue, which is the one you would find into the Earth. If you have other molecules, you find a different ratio of the molecule, you will be able to tell something as well fascinating about these other planets, but it may not be life. You see, there is so much to do, but there is a very change of paradigm here that is going on. Is we're going to do the kind of study we used to do on planet on the solar systems. We're going to do this on other planets, and we have an infinite number of possibilities. And we will be able to explore this amazing diversity we're seeing right now. And eventually, one day, we will find something, and something which is awkward enough such that we cannot explain it by the geophysical mechanism. And we will have to consider that this is a possibility that we may have found life here on that planet. I would like to thank you here. I hope I gave you plenty of good ideas, and I hope I convey to you how much fascinating is this field of research. Thank you very much.
Thank you, sir. Thank you very much, Professor Didier Queloz. Questions? You are taking questions, Professor?
Yes. Yes, I have time for questions.
Yeah. Questions?
If anyone has any questions, please send it in the chat box.
Someone raise a hand, a blue hand.
Yeah.
Please. Yeah, Professor Sengupta sir, unmute yourself.
Hi, I'm Pearl from the New Indian Express.
Yeah.
I'm sorry, am I audible?
Pearl from New Indian Express. You can talk. You can ask.
Yeah. Hi, Dr. Quellos, nice to have you at the conference. So we've been having quite a few space missions that India is also looking forward to, including, the another moon mission, and we have Venus mission lined up, and we have the solar mission. But the really pressing question, all in all, always is that what are the implications of this to a planetary life? The life that we have on the planet. Of course, there are. It has been suggested that most of our interplanetary missions are supposed to help with the scientific exploration, but with a lot of sustainable development goals still to be reached. If you could just run us through what are the advantages for us out on Earth. Second question is if you could just outline something on the Artemis mission and what it would mean for the global scientific community and for the non-scientific community.
Okay, thank you for the question. So I didn't talk about the planetary exploration mission, but they are really essential. The reason why they are essential is other planets in the solar system are the only planet where we can really go and bring back stuff. And there's a point when to study in detail, you need to bring the rocks back. So it's absolutely essential and fascinating to go and to try to get back something from, well, we can think about Mars because it's the most obvious planet. I mean, Mars, we know the first billion years old was very similar to Earth, had plenty of water, and it's very likely that we should have expected to have life development on Mars as well. At the same time, we had the early stage of Mars, of development or life on Earth. So since that stage on Earth is erased by the plate tectonics and we have essentially no clue at all what was going on, Mars is a chance for us because everything stopped at that time to have some imprint. And we are very keen at getting the detail of the geophysical analysis of the rocks that we'll be bringing back. I don't really think we're going to pick life into these rocks, but my hope is we're going to find early ingredients, or say building blocks of the chemistry that have enabled life, and we can compare with what we expect is the origin of life on Earth. Venus is fascinating because Venus was like the Earth. I mean, we know that possibly 1 billion years old ago, it was also a blue planet. So Venus now is not at all in this situation because it's a fully greenhouse dominated atmosphere. You cannot be there, you cannot live there. The reason why, because the plate tectonics seems to have stopped. It's an interesting question why it stopped on Venus and it's still going on Earth, because if we stop the plate tectonic, I mean, we'll end up like Venus as well, because we don't recycle the CO2. And I think there is still a very open question is what is exactly the nature of underneath of Venus? And nobody knows anything about this because it's a difficult planet to land on. Now, we have also the satellite of some giant planet in the solar systems, Europa, with this very thick ice crust, and a lot of people are dreaming about drilling into it and having a look what's underneath, because there are a liquid ocean behind, it's pretty clear. So what exactly is going on? And there are also a lot of interest about Enceladus, because Enceladus, we've seen some kind of jet stream out of the planet, and we know there are activities on these planets, and there is a hope that maybe there has been some biological development. So I think this is part of this big question mark about the origin of life that can be combined with ground lab work that people is doing in the lab right now. There are teams in the world trying to reproduce from the biochemistry first principle the origin of life, trying to make life. How could you build up a kind of proto-RNA without any enzyme? And it's just starting from the bare chemistry. And that all this is fascinating. And I'm very looking forward to Mars missions, because there are people arguing that maybe life can can spread between the planets in the solar systems, and you can imagine you start somewhere and you can have the life going back and forth between planets, and you may find the similar kind of structure we had on Earth. And the question will be, are we coming from Mars or are we going to Mars? So that's kind of a very open question. So I think this origin of life problem brings fascinating number of chemistry, and also open up a whole new domain of the biochemistry, which is the possibilities that we understand so much the origin of life that sooner or later we will be able to make life. It's kind of a very fascinating prospect, as it's also maybe a scary prospect, because we are master of the death, because we know to kill ourselves. We have enough nuclear weapon right now to kill, but sooner or later we may be able to create anything, because to be able to make life. So we are fascinating species, sometimes a bit scary. I'm not sure I can answer the second question because I don't know the mission you're mentioning.
Okay, thank you. Baswaraj Kagali will unmute. Baswaraj Kagali.
Can I come up?
Yeah. Sujan Sengupta can ask.
Hi Didier, this is Sujan Sengupta working in Indian Institute of Astrophysics. I collaborate with Joanna Tinetti on aerial project and on polarization. Okay. Yeah, I think we have met earlier. Yeah. So how is Michelle doing?
How is mission 3?
Yeah, my question is that since you have mentioned about the satellite in solar system, so what about discovering exomoon? Maybe an exomoon in the habitable zone around a Jupiter type of planet around in the habitable zone could harbor life as it is predicted in science fiction like Avatar. So what is the status? When are you going to discover the first exomoon?
Yeah, moon are fascinating because they are predicted. If you look at the formation of giant planet, you have to have moons. That's why all our giant planets have moons. So you expect to have moons on all the giant planets. So that's really not a surprise. No, the big question is, what does it mean about the nature of these moons and whether you have the condition for life? I mean, frankly, I don't know, but I know that some people are looking for moons because in a way, it is predicted and we really want to find moons. Now, the moon you have in mind are much smaller than the planet that we can detect. I mean, a moon that is the size of the Earth would be a monster moon right now, and we can barely detect an Earth planet. So a moon will be smaller and will be even more challenging. So if you think about detecting a moon like the moon, which is a big one, I mean, the moon, our own moon is really a big one already, it will be a really big challenge, but sooner or later, again, it will happen. And since we're all expecting the moon to be there, your question will be more than valid, because if you have a giant planet in the habitable zone and the moon is rocky, well, so what? I mean, you may have clearly life, development on any of these moons. It's certainly a possibility.
So what are the methods that you are following? Are you following anything? The radial velocity can detect the moon?
No,
I know that
the radial velocity cannot detect it. The only way to detect it right now is to use the transits, because what happens is you can be lucky and just find transiting moons, or you can hope to detect timing variation into the timing of the transit. That's really the only way to detect it. The effect of the moon on the star, because remember, we're only measuring the star, is really tiny, tiny, tiny. You barely see it. And the effect of our own moon orbiting the Earth on the sun is almost invisible. So it's really a transit techniques.
Okay, good. Thank you. Baswaraj Kagali.
Yeah, thank you.
Vijay Kumar, go on.
Sir, my question is a sort of general question, like the evolution of the Earth's atmosphere, and the carbon was not in this abundant level earlier. Can you tell me what epoch, what time scale back the carbon was less, and that now has led to the evolution of the human being, intelligent human being?
Yeah, So I think you have a very important point here, which is very important to remember. When you look at a planet, which is a rocky planet, you don't have a single atmosphere. You have a primary atmosphere, and this atmosphere is evolving. It's evolving on for two main reasons. The first one, you have all the impact, meteoritic impact, that is falling on the atmosphere. You can have a major impact that is absolutely vanishing the atmosphere. Early on, you can have a lot of CO2 atmosphere because that's what you have for free when you start building a planet. And then you have a major impact and boom, all the planet is gone. So you can have really major impact, and these impacts are not unlikely when you form a planet, because at the beginning of the life of a planet, if I can use the term life of a planet, is there's a lot of impact falling on the planet. And the moon is one of the examples of what happened when you have an impact. Now, what you have later on, it depends on the nature of the planet, because the atmosphere you're getting on a rocky planet is the outcome of the geophysics of the planet. So depending of exactly is it the planet, if the planet is still a little bit molten or a lot of lava or not, if it's solid, depends on the cycling, depends how you can recycling everything, you end up with a very different kind of planet. So this is not an easy question to answer. What we've seen on Earth is there has been a dramatic event, which is the ground oxygenations. At some point, the oxygen has built up like crazy, and we end up with this very massive amount of oxygens. And we do believe this is the outcome of a lot of events at the same time, but essentially the kind of explosion of life on Earth, an explosion of the oxygen and productions. Now, I don't really know if the timing will be exactly the same for a planet, but I don't really care, because I think what is relevant here is to study exactly what you mentioned. When you pick a planet, you should really be able to look around different time scale. You should find out the time of the systems, and we have some idea how to do that. And we should ask yourself why the atmosphere is like that. It may become quite difficult for a single planet, but let's imagine you have hundreds of planets. Then you have a global picture, kind of statistical picture you may be able to build up, and then we would understand how the Earth is sitting compared to all these other planets. So the Earth on that respect is very complicated. If you look at the Neptunes and Jupiter, it's a bit easier because they retain the kind of the information they have from the way they've been formed. So now we're essentially focusing on these planets because it's a bit easier. Jupiter is essentially it's a trap. So when you study Jupiter, you understand the formation of a system. So you can use the fact that a system would have Jupiter planet on Uranus, Neptune planet, and as well the Earth, to combine the knowledge, because you will have the pristine information of how the system was at the early stage by looking at the atmosphere of a Jupiter. You will understand the formation process, how you build the planet by looking at Uranus and Neptunes, because they retain this information to some extent, and they have also the mixing of the infall that will be a bit more severe. And then you have this extreme case of the rocky planet that has been completely changed. You may have a primary, secondary, tertiary atmosphere, and you will have to find out. So this is a fascinating and difficult topic, but that's what everybody will be doing in the next 50 years, I'm pretty sure.
May I ask now?
Next
Thank
question.
You so much, sir. Thank you.
Which combination of atmosphere molecules would provide a signature for life? Baswaraj Kagali.
Yeah, well, this is the $1 billion question here. The only thing people are pretty sure, if you find something exactly the same than the Earth, there is a good chance that there is life. But as soon as you deviate a little bit from that, well, you will end up with endless debate at this point, because you need to explain what you found. And right now, I'm not sure everybody agrees on that. So it's a very open-ended question right now. But that's the reason why it's a fascinating question for young scientists, because there is everything that can be done here.
Next question is, would you expect life forms that are based on carbon chemistry like Earth, even in exoplanets? Could there be a silicon-based life system?
Yeah, I know that people are mentioning this possibility. So everything is possible as far as you don't break the rule of physics. But you have to admit two things. First, carbon chemistry is very easy. And when you look at a molecular cloud and anything, you'll see plenty of fascinating carbon chemistry. When you look at a comet, you see some basic amino acids. They can easy to be done. So carbon is everywhere. It's more difficult for silicium. So the probability that you would arrive different from carbon is very low just on these very basics, because there is plenty of carbon. Now, carbon and water goes very well along, and there is tons of water everywhere. So this is so easy to make chemistry with carbon. Why would you do something more difficult? So I'm pretty sure that life has followed an easy path and the easiest possible path. So I would not expect to be life different from carbon on this first principle. But on some case, maybe you end up with something very bizarre. But I can tell you, if life is very different from carbon, good luck to find life, because we don't even know what to look for.
Okay. Is there any evidence or possibilities of plurality to singularity and multiverse to universe?
Oh, okay. So the multiverse, it's a very open question, which is based on theory. And of course, it's possible. There is a prediction that if universe are eating each other, so if you have many bubbles, and some point they will start to cross each other, there is some prediction on that. So we're looking for that. People are looking in the deep universe to find the probability that there is another universe with different rule of physics that is eating us. So far, we have not found any. So right now, they don't exist, because science is based on fact, not on theory, but it is still a possibility. Now, what about the other questions? I just missed the other questions.
How much amount of phosphine should be present in an exoplanet to interfere with the existence of life form?
I see you're quoting the Venus story. Yeah, okay. So phosphine is a production of life. It's pretty clear, but that's not the only way to do it. So to really understand phosphine, you need to get a complete picture of the geophysics. So that's a bit the challenge of Venus, because Venus, it's so close. It looks very simple planet, but we know very little because we have not been quite often to Venus. I think Venus has a lack of knowledge. And I hope that with the new material, we will be able to make spacecraft that will survive the acid on the surface of Venus, and will be able to study Venus in great detail, because I think it's a very fascinating, the phosphine discussion is very fascinating. Right now, the consensus is a bit weaker. It's not very clear whether they have really seen phosphine, and people are debating because it's a difficult measurement. But the prospect that there are phosphine on Venus, I think, is a fascinating prospect. And the idea that there may be life on Venus is very thrilling, while it may not be the reality.
Why are we looking at life on other planets with reference to Earth? Couldn't there be any other forms of life?
Well, that's it. The question of form is interesting. Chemistry is the same everywhere. So the question is, how come do we get these 20 amino acids on Earth? And the possible way is, this is the more likely chemistry, the building blocks for life. So there is a big chance that the amino acid will be the same a bit everywhere, given you have the same conditions, because we know the chemistry that produced them, and it seems to be kind of a massive chemistry. Now, from the amino acids, whether you will get the same kind of material being built up, it's not very clear. Whether the RNA is the only way you build up the RNA, or you can have other kind of RNA built on the same amino acids, nobody knows that. Hopefully the chemistry should tell us in the future. I would not bet too much on that, but what I would definitely not bet is the probability for life to become like us. I mean, the probability for life to evolve into animals came very late in the story of life. For a long time, and life was very simple. And then if you look at the basic element of life, which is a cell that we find everywhere, and every living creature on Earth, except the virus, they have the same structure. And this is the outcome of a couple of billion years old of evolutions that make the cell so perfect, with all the tricks that the cell is using to function. Now, whether the cell has to be exactly the same, maybe not, because maybe the cell has evolved on the condition of the Earth. If you change a bit the conditions, you may end up with a different mechanics, and with a different mechanics, you may end up with a different kind of animal, completely different. So I think you can imagine whatever you like. If you start deviating from the building blocks, it's like if you start building a building starting with one kind of concrete, or if you change and you start with wood, then you will still have a building at the end, but the building will be very different, because it's still the same functions, but because the unit is different, then the way it is built up is different. And I think we're debating on that right now. And I really hope that exploring the other world will help us to understand how far or how different or the building blocks of life? Are we all the same, or are we really different from the very beginning? And I think this question we may answer in the next 100 years.
Yes, sir. You have built custom instruments for recording your observations. Can you tell us what kind of technical difficulties, obstacles you have faced that led you to design your own instruments?
Well, at that time, nothing was known, and we have to be very creative in the tricks we have been using, but we use a couple of new development. The key development was optical fibers. Optical fibers started to be used for astronomies, and they turned out to be a key ingredient because to stabilize the flux and the entrance of the spectrograph. Now, it was the beginning also of the electronic detector. The CCDs were starting to be used in astronomy. So we used the CCDs, the best we could use at that time. And opticians started to develop a design which was more compact for building high resolution spectrograph. And we implemented such a design due to a new component, which is called a high angle gratings that was started to be available at that time. So we put that together and we used all the tricks we could to control the stability of the instruments. And that was not easy. And we had to develop a brand new kind of software to do that, to make sure that what we would measure would make sense. And that was essentially my job. So we had to go through a couple of tiny problems one after one, but essentially we could do that because of the optical fiber, the CCD detectors, and the new kind of design that was available in optics. And we were the first one to implement all of them together. So because we took all of them together, it was so new that it created a new kind of instruments. And now this instrument has plenty of many copies. So there is no, I think we're talking about the 4th generations of fiber-fed stabilized instruments, which is based on all the systems, all the technology that we built 25 years ago to build the spectrograph that was called LOD.
What are the implications of the Artemis mission by NASA?
Could you remind me what is Artemis? I forgot. Which one is this?
Okay.
I can't remember what is Artemis. I can't remember what is Artemis mission. Sorry, there's so many. I got lost.
Okay. Are there any clues for the presence of other Earths nearby this Earth?
Yes or no. We have Earth kind of planets, but they are very close to the star. There is something that is not that far from Earth orbiting Proxima Centauri. We know there is a kind of Earth planet, but we're not sure it's really rocky at this point because we only have the mass. So there's a couple of clues here and there. We have the TRAPPIST system. We know there's 3 or 4 Earth-like planets there, but the star is very, very tiny. So it's a different kind of planetary system. It's kind of a mini planetary system. So we have a couple of systems here and there, but they are in a way very different in some aspect, but we know they are really rocky planets on the systems.
With regolith on moon and difficult to reach on far side or southern region, still you do expect a colony on moon?
Well, moon is interesting because I think going for the moon will allow us first to study a bit more detail the moon. The moon is still an imprint of the formation of the Earth early on. I mean, the moon was created early on at the formation of the Earth, and I think there is interesting to study on the moon. So I'm very glad that we're going to the moon. In terms of astrophysics, the far side is fascinating because you're protected from the Earth essentially, and you can study the deep space. So there is a couple of ideas to have radio antennas, I think, on the far side of the moon, looking for the origin of the universe, which I find fascinating. So of course we'll go there. I think technology now has become much cheaper, and I think we can send robots. Robots are becoming more and more clever, so we don't have the risk to send people there. And I can well see a fully automatized kind of site over there on the moon, doing a lot of fascinating measurements, helping us to understand the origin of our own system, origin of the Earth, and also trying to get a picture of the very origin of the universe.
Yeah, Artemis is the NASA's human spaceflight program to put women and man on the moon by 2024.
Yeah, why not? I think it's a dangerous place to go, but if they really want to go, they can. But I think it's very dangerous. It's better to stay on Earth. It's very dangerous to go to the moon.
Okay.
I will have to leave in 2 minutes just to be aware. So maybe one question.
The last question, could astronomy help in detecting biological molecules?
Yes,
I don't think
Could radio astronomy help in detecting biological molecules?
Right. So the radio has detected plenty of molecules in molecular clusters. So we do have a very interesting, fascinating carbon chemistry, which is due to the fact it's very cold and it's very low gravity. So there is a kind of a very elongated chain of carbon that is been detected in the space, which cannot be produced on Earth because of the very special conditions. I mean, universe provide the best lab in the world because it give you the coolest, the biggest, the highest gravity, the least gravity. You can have all the conditions. So yes, there are molecules, but these are not molecules of life. They are just biochemistry molecules, very special molecules that are being produced because of the condition that you experience in the space are very extreme, and you can build up a kind of a chemistry which is very slow and also under very intense UV radiation that is very interesting to produce the chemistry here.
Yeah, last question, sir, Professor. Would TMT help in detecting more exoplanets and life there?
Sorry, what? Could you repeat the question? I missed the beginning.
Would TMT help in detecting more exoplanets and life there?
So what is going to help us? Is it the questions? Or?
TMT.
Oh, the TMT, the telescope, TMT.
Yeah.
Yes, all these big telescopes and TMT, ELT, there is plenty of them that is being built right now, will open a new area because we should be able to do this kind of spectroscopic measurements I mentioned. So I hope that we're using the big size of these telescopes to try to detect the tiny flux we have for some of these planets. Yes, we're going to make progress, but always the progress are tiny, everyone, day by step, but every step counts. And there's a point when the step is such that you reach a kind of a threshold, then you open a new window. And we don't really know when is this next threshold, but certainly having better equipment helps. And again, this is one of the big push for a lot of the future generations, trying to have equipment that help us to understand the atmosphere of these planets.
Thank you. Sir, I have very simple question, that how long life would exist here on Earth, sir?
I don't know. Well, I think we should be more careful.
Okay. Professor Vijay Kumar Dadmane, please deliver the vote of thanks. So thank you, Didier Fellows. I'm delighted. Actually, I enjoyed listening to your talk for nearly an hour. And I would hope that you will come to Bangalore and see the climate and enjoy this climate. And also, I mean, the feel for the astrophysics that is taking place, the development that are taking place in the Department of Physics in Bangalore University. Thank you, Didier Fellows. And now the vote of thanks by Vijay Kumar Dadmane.
Professor Didier, sir, at the outset, I thank very profusely to our Honorable Vice Chancellor, Professor Venugopal, sir, for accepting our proposal to invite the Nobel laureate for the first time in the history of the Bangalore University and also in the history of the Department of Physics, that we have invited a Nobel laureate for this such kind of multidisciplinary international conference. And I thank Professor Didier firstly for accepting our invitation. Our desire was to invite you physically here to the Bangalore University, but due to the situation that we have ended up in inviting you online, and we hope in future we would like to invite you to Bangalore University, sir. And I would like to tell you that Bangalore University is the only university in Karnataka and only few universities in India offering astrophysics as special course to our MSc postgraduate students and doing research in physics, and due to collaboration with the Indian Institute of Astrophysics. And I wish sometimes you do come to Bangalore University. And with this, on behalf of the organizing committee, Professor Convener, Professor Krishnamurthy ji, and all the coordinators, and all the teachers, and our Vice Chancellor, I thank you very much for accepting our invitation, delivering very scintillating and exciting talk to all of us. Thank you very much, sir.
Thank you very
Namaste.
much.
Thank you, Didier Fellows.
I will come.
Good evening.
I promise.
Yeah. Thank you, sir. Thank you. Namaskar.
Yes. See you. Good evening, Didier Patrick. Yeah, we'll be in touch.
Sure.
Okay.
We
Sir,
shall.
one more
Thank you.
question, sir. Kindly, can you give your review article for some publication in our newly launched journal by Bangalore University of this
Yeah.
talk? Can you send a review article?
Yeah, send me an email what you need exactly.
Okay. Thank you.
Yes, sir.
Thank you
Bye.
very much, sir.
Thank you.
Bye-bye.
Bye-bye.
Thank you.